Hello, is this thing on? Let me see. Is this on? Is this on? Yeah, she's on. All right. Uniform line charge is located along y equals 2, z equals 5. And we want to know what electric field is at a certain point. So we have a point at 1, 2, 3. So we have a point somewhere over here. And we have a line over here. -2 and 5. So it'd be like -2, 5. Like it's growing along the x-axis. So we have an infinite line of charge growing like that. So whenever you're doing something like this, I like to visualize the problem first, kind of like what I just did, but also throw it into 2D sometimes because that'll help you understand what you're really looking at. So you have a line of charge here, right? It's growing, and obviously this charge is this line of charge is gonna push the point down, in some direction like that, and we want to find out what that looks like, how strong it is, which way it's headed, kind of, that kind of situation. So the first thing to know is, since we're dealing with the infinite line of charge, I'm going to draw it over here. I'm drawing the same thing in 2D, right? So you have an infinite line of charge. And point here. All of the charge coming from this point, like in this direction, this vector, and all the charge coming down here, the horizontal points cancel. You've probably done this a little bit more in physics already. So the horizontal components will all cancel as you go through this line of charge. So you'll have a direction that's going directly right here, right? So what does that tell us in this situation? Well, if we have a line going along the x direction, we know that there will be no component of x, because that's essentially what this would be like. This would be the x-axis up here. So all the vectors that are pushing up this way are going to cancel with the components that are going down that way. So you're not going to have any. What I'm getting to is that you're not going to have any values of x. Okay, it's important to know. It's good to think about that stuff before you do the actual math, because then if you do something wrong, you know you're screwed up. So what equation will we use here? Well, I know the equation, buddy. That's why I'm doing this video. You're using the line charge equation. This is charge density, charge per meter. So yeah, that, and then 2 pi epsilon naught r squared times, this is magnitude of r squared, but it's, times the vector r. So this is like a modified version of Coulomb's law. This is still like a unit vector, kind of. And there's the r here, and the r's, so there's your equation, right? So the first thing we should find out is, well, first we can make a solid definition of what our line is. So we'll call it line A, and it has the parameters x is equal to any value x, y must equal -2, and z must equal 5. So it grows, as you could tell, y and z are set. You can't really change anything about the z, y coordinates. X can be whatever the hell it wants to be. Now we have our point P at 1, 2, 3. So finding our r vector is pretty simple. You're going to have r is equal to the AP vector, so point P minus this A value. So like I was saying, for the x component, you're not really going to have an x value, because remember I was talking about how they cancel, so that's going to be 0. Another way you could do that is you could say, well, the only point that really affects it is the point at x equals to 1. That's the only point that really has its own well, not even really. No, just know that all the x components cancel. You just kind of have to observe that and know. At least I don't know how it be done mathematically, at least. And this would be 3 minus 5. So I'm just taking p minus point a, or the line a. So r would then equal 0, 4, 3 minus 5 is 2. Absolute value, or magnitude rather, would be 4 squared. 4 squared, 16, 2 squared, 20. So that'd be root 20. And then that leaves us to this squared would be 20. So then we plug in this equation, we have everything we need now. E sub p, that point p, we'll call it E sub p. Rho L, we already know rho L, 16, yep, 16 nanocoulombs per meter. The units don't matter too much. You should know that they result in no cancel and shit. R squared is 20, sorry. And then you would have this vector right here, 0, 4, 2. So then that would give you, let me pause this real quick. Can you pause these things? I wonder if you could pause this shit. Guess not. Trying to find out what the value is. Well, you just plug it in, you get some number here. So now let us do part B. Part B is pretty fucking hard, not gonna lie, because you have to kind of really get what's going on. So find E at that point in the z equals 0 plane where the direction of E is given in 1/3 AY minus 2/3 AC. So sorry, I lost my thoughts. So you still have the same line. Going in that direction. Do that again. And now it wants to know where it's going to be if if it's at the z equals 0 plane. So the only real information we have, this is like the z equals 0 plane. So we have the direction. We have like one kind of hint, right? So our one hint is that the direction of our E field is 0 there, obviously, because we talked about that already. 1/3, 2/3. Okay, so that's our hint. How else would we want to start this? We could start this by, you would, the way I did it was subtract A by, where did I put that at? Right here. So you could start with a generic point, we'll call it B, and that's equal to X, Y, Z. So B represents any point. You could pick a freaking point, doesn't matter. So what would AB be equal to? Well, AB would be equal to, I'm just taking this line equation here and subtracting b by the line equation. So it'd be x minus x, y minus -2, and then it'd be z minus 5. So for any point, we would have something of this form: y plus 2, z minus 5. Well, this really doesn't tell us much, right? Because you still have a y as a variable, and you still have z as a variable. Well, we know one thing. Z is going to be equal to 0, because we're in the z equals 0 plane. So that at least tells us ab sub z equals 0 equals 0, y plus 2. And then this will be a 0, so that'll be a -5. So there you go. You have that part. But now you have to find out what y equals if you want to get anything meaningful, any meaningful point out of it, because if not, it'll be dependent on y, right? Well, that's where that vector up here comes into play. That's where this comes into play. So we know that vectors are just kind of like if you have a graph like this and you have a vector in this direction, if you scaled it, it still kind of describes the same thing, right? Like you could scale it in different ways and it's not going to change anything. What vectors really tell you is how the variables relate to each other. So, you know, for every 1x, like a 1-to-1, this is like pretty much a 1-to-1 vector. Like every 1x, you'd have 1y. So it's like related. They're related to each other like that. This would be like a 1-1 vector. And if you had like a 2-2 vector, it's kind of the same thing. It's really not any different. So knowing that, we could take a proportion and say, okay, well, this is 0, 1, 3, 2/3. Oh wait, I think I did that wrong. I think this is -2/3. Yep. There's supposed to be a negative there. I just remember from the problem doing it before. -2/3. Scale it up. 0, 1, -2. Now we know the relationship between z and y, right? So the z component of this vector would be it'd be the y component times -2, right? Or you could say, yeah, you could say like the y component is equal to the z component over a -2, right? So that's the relationship between those two components of the electric field. So what does that tell you? Well, we have these components here. So the z component's -5. That's equal to -2y plus 2. And now we have a simple equation we could solve for the variable, right? That'll be a -4, -2y minus 4. And that'll be a 1, and that's over, and that'll be a 1/2. Well, screw it, I'll just write it out. -1 equals 1/2. Okay, so now you're kind of at the finish line here. Now you could put, I'm doing red now, AB without any variables will give you 0. 1/2 plus 2 is 2/4 plus, wait, 1/2 plus 2 is 4/2 plus, it'd be 5/2. And then -5. Then you can find the magnitude. Shit, I'm running out of space, people. Magnitude would be something here. So that would be like 25/4 plus 25.
25 over 4 plus 25.
25 over 4 plus 25. 25 over 4 plus 25. 25 over 4 plus 25. 25 over 4 plus 25. 25 over 4 plus 25. 25 over 4 plus 25. 25 over 4 plus 25. 25 over 4 plus 25. 25 over 4 plus 25. 25 over 4 plus 25. 25 over 4 plus 25. 25 over 4 plus 25. 25 over 4 plus 25. 25 over 4 plus 25. 25 over 4 plus 25. 25 over 4 plus 25. 25 over 4 plus 25. 25 over 4 plus 25. 25 over 4 plus 25. 25 over 4 plus 25. 25 over 4 plus 25. 25 over 4 plus 25. 25 over 4 plus 25. 25 over 4 plus 25. 25 over 4 plus 25. 25 over 4 plus 25. 25 over 4 plus 25. 25 over 4 plus 25. 25 over 4 plus 25. 25 over 4 plus 25. 25 over 4 plus 25. 25 over 4 plus 25. 25 And then you would have your equation again, E equals rho L over 2 pi epsilon naught. You would have this here, or this, remember this would be squared because in the original, in the equation here you have a square, not this. So you wouldn't have that square root. Plus 25. And that would be times this vector. Negative 5. And there's a 0 there too. So I'm not solving that. I just got Chipotle, or no, I got, oh no, I didn't get beer either. Damn, that kind of sucks. But yeah, I'm kind of getting hungry, so there you go. Hope that made sense. It's like, it's a bit complicated with this part. You just have to realize, like, you're kind of comparing the two vectors and you know one subcomponent, so you plug that in and solve for the other. But there you go. Peace.